Hey guys, we are looking at the second reaction today. This is decomposition reaction. Well, as you can see in this reaction, doesn't that look like the backward of synthesis reaction? And in some cases it is. It is the backward. It is synthesis, written backward. If you remember, synthesis was, two become one, and decomposition is basically one breaking up into two or more. Now, let's fill in these blanks, okay? So make sure you're in the right page, and let's take a look at decomposition reaction in terms of what it is and some of the examples that you are required to know. So first things first, how does it work? How do you identify that this reaction is a decomposition reaction? Well, a decomposition reaction involves the breaking up of if you look at X and Y, I'm sure you guys all agree that this has to be a compound. Can't be anything else, right? You wouldn't have an element being, having two elements bonded, and then that's not really an element. Well, you can say smaller substance, you can say simpler substance, okay? And does it have to be elements? Do X and Y have to be elements? And the answer is no. They can be either elements or compound, just maybe in a smaller scale, okay? Where, of course, XY is a compound, again. And X and Y may either be elements or compound, depending on what it is. And some of them can be can be difficult to predict. Okay, so let's take a look at a few examples right here. The first example is really the reverse of the oxide example we've looked at in synthesis, where you have a metal oxide breaking up into a metal. In this case, it will be mercury. Doesn't matter which mercury. Do we have to indicate that, this mercury is a +2 mercury? The answer is no. You don't need to do that. Okay, and it's not very important for you to do so. Mercury is just mercury. Okay, so just like in synthesis, where you add mercury and oxygen to give you metal oxide, in this case, the metal oxide will decompose to give you mercury and oxygen. Now, I can tell you right now, these reactions are usually not spontaneous. There has to be some sort of spark to make this happen. A catalyst, or maybe heat. And these will be indicated on top of the reaction arrow, which we will see later, okay, sometime down the road. Now, the same goes with the non-metal oxides. The non-metal oxides will break apart to give you your non-metal. In this case, it's a gas, hydrogen gas, and water. Okay, so in terms of the catalyst to make this happen, if you remember back in the days, we said that in order to split water into its elemental form, which is hydrogen and oxygen, we need electricity. So we plug this thing into this thing called electrolysis, and we watch how water, we're creating bubbles, and these gases are collected on opposite side of the apparatus. We test the fact that this indeed was H2 because it gave a little bit of an explosion, and we test the fact that O2 reignite a glowing splint, which is an indication of flammability. So this is obviously something that you might have seen back in the days, via electrolysis. Now I have some more that I want you to add. I think there's a little bit of space there. I want you to add this. Hydrogen peroxide. Hydrogen peroxide. Well, it can be sodium peroxide. It can be any peroxides. But when peroxides decompose, it actually decomposes to give you a non-metal oxide in this case, and oxygen gas. Okay? Now, if that H right here was replaced by, let's say, a sodium, then I guess you would have a metal oxide instead of a non-metal oxide. But this is more popular in terms of being realistic. Okay, seeing how hydrogen peroxide can actually create oxygen gas only under a special catalyst known as manganese 4 oxide or manganese dioxide. Okay, so this right here is called a catalyst. A catalyst's job is to speed up a chemical reaction, whereas without it, this reaction might not happen. Or it may be so slow that you may not see anything happen. A reaction that is slow and you can't see what's happening is not a fun reaction. So in order to see hydrogen peroxide bubble up, put some manganese dioxide in there. Okay? Now, one more thing about a catalyst. A catalyst is not part of the reaction. Well, at least not, part of the reactants and products. Okay? It's not really consumed by the reaction as well. So what that means is that you will not, when a catalyst is done finishing its job, it still remain as a catalyst. So MnO2 remain as MnO2. Okay, it's not going to be part of H2O2. As you can see, there's manganese in here. You don't see manganese in any of the products, right? That's because manganese is not part of the reaction. It's a catalyst to make sure that this reaction happens at a short period of time. Okay. All right. That's something that we will stress a whole lot later on when we look at different types of catalysts. There are homogeneous catalysts, there's heterogeneous catalysts, and these are things that we will talk about later on. All right, so let's talk more about other decomposition reaction. What I have here is a carbonate, okay, a metal carbonate. You can also have a non-metal carbonate, and it will actually do the same thing. Okay, so when you have a metal carbonate decomposing, okay, what you'll get is a metal oxide, like calcium oxide, and most importantly, they generate carbon dioxide. This, I guess, is the fizz that you see. Okay, whenever you have a carbonate being exposed. Now, one example that's popular, I'm sure you guys love it, is sodas. Okay, pop, Coca-Cola, Pepsi. My favorite is, actually I don't have a favorite. I guess I like root beer every now and then. Okay, well, one of my least favorite is Dr. Pepper. I really hate Dr. Pepper. I always thought that cherry cola really not supposed to exist, but it does. I'm sorry for those of you who loves Dr. Pepper, but I'm just not one of those. Okay, but I do like Coke Zero for some reasons. I do like Coke Zero. All right, enough of soft drink. I kind of want one right now. So when you open up a soft drink, obviously you hear fizz, you see fizz. Of course, that's what you're seeing. Of course, is the generation of carbon dioxide. Okay. Also, the reason why if you drink them, you burp them. Okay, because your body's trying to get rid of this carbon dioxide. Okay, via, of course, gas regurgitation. Okay. Try not to make it too loud. Okay. All right. So, as I said, you have metal carbonate decomposing to give you metal oxide, always a metal oxide, and carbon dioxide is always going to be carbon dioxide. I'm going to do another example down here with a non-metal oxide. This is hydrogen carbonate. Okay? And with hydrogen carbonate, it too okay, wants to decompose. In fact, this reaction is quite spontaneous, especially when it's in our body. H2CO3 decomposes to give you H2O and CO2. Again, CO2 is generated, just like what we saw before. But instead of a metal oxide, in this case we don't have a metal, it's hydrogen in place of a metal, we have a non-metal oxide in the form of water. Okay? It's a very classic example. It's a very important example. Now, here's another example right here. This is metal bicarbonate. Okay? HCO3 is one of the things we call acid salt derivative known as bicarbonate. And this whole thing is known to be calcium bicarbonate. When calcium bicarbonate or any metal carbonate decomposes, it actually gives you three products. They are metal carbonate, water, and carbon dioxide. These are a must. You're always going to get water, you're always going to get carbon dioxide. Okay? This, of course, depends on the metal. In this case, it is a calcium bicarbonate, so you get a calcium carbonate. So if I give you an example, such as sodium bicarbonate, in case you're wondering, sodium bicarbonate is what we call baking soda. We put that in cakes, we put that in bread. The reason is very simple, and it'll give it a more of a fluffy type of texture. Okay? Who wants to eat cakes that ain't fluffy? Okay? It's disgusting. It's gross. Nobody wants to eat that. You know, why did it turn fluffy? Why does it have air packets? Well, it's because when we put sodium bicarbonate under heat, that's what that triangle is. This is delta, okay? In mathematics, you know that's the change of, the difference of. But in chemistry, when you see this on top of a reaction arrow, that means heat. Okay? Is it a catalyst? Of course it is. Speed up this reaction. You think baking soda is going to decompose without heat? That's not going to happen. That's not going to happen at all. All right. The question is, what will happen under heat? So sodium bicarbonate under heat will give you sodium carbonate. Notice, cross rule applies. Okay, cross rule applies. There should be a 2 here because carbonate has a natural -2 charge and sodium has a natural +1 charge. Cross them, you will get Na2CO3, and that's not anything you don't already know. What else? Well, water and carbon dioxide is going to be generated. Okay? I guess the water will give your cake a little bit of a moisture because we also don't like our cake dry. Some do. I don't understand. I like my cake a little moist. Easier down the throat. Not throat, sorry. Easier down the esophagus. You have to be careful in terms of your physiology. And carbon dioxide, okay, which makes the air packets in cakes and bread and stuff like that. Okay, give it more of a fluff. Anyway, hopefully you understand this whole thing. It's not that hard, right? All right, I have a couple of more that is not on this page that I want you to note. Let's put a little barrier here, and let's do this. So I have right here a metal chlorate. Okay? Metal chlorate decomposes to give you metal chlorides plus oxygen gas. Okay? So if there's a case where you need to make oxygen for maybe a combustion reaction, this is it. This is the type of reaction that will make oxygen gas pure and highly concentrated. Let's take a look at an example. An example could be a potassium chlorate. Okay, we call this a very strong oxidizer. And we'll know what that means later. And that will decompose to give you potassium chloride and oxygen gas. And remember, a reaction is incomplete unless you balance them. So let me see those practices. So as you can see right here, there's a metal chlorate, ClO3 minus. That's a chlorate. This is a metal. So metal chlorate decomposes to give you a metal chloride, okay, and of course oxygen gas. Again, this reaction requires heat in order for it to happen. All right, I have another example. Okay, let's use another color here. This is also a very important example. Okay, we have metal nitrate. Okay, metal nitrates decompose to give you metal nitrite. Again, releasing more oxygen gas as a product. An example will be sodium nitrate. Okay, this stuff decomposes to give you sodium nitrite plus oxygen gas. Right? Hopefully, this is not something too difficult to understand. And again, it's probably wise to put these two here, okay, for the purpose of things being balanced and things being complete. So here are some decomposition reaction that I really need you to know, okay, to move on to the next topic, which is, of course, stoichiometry. All right, let's take a look at the next reaction. Okay, we're going to do a couple of reactions today. So we've looked at synthesis. We looked at its opposite, kind of like the opposite, decomposition. And let's take a look at this one. I'm going to skip these ones a little bit because we're going to go and look at combustion. Okay, which is great. The reason why I want to look at combustion is because combustion deals with reacting with oxygen. This is kind of related to what we see here, we saw here with decomposition reaction, because if you look at decomposition reaction, especially these ones, and these ones, they all generate oxygen. What's important about them is that these oxygen can be used to drive this reaction. We call that, of course, stepwise reaction. Okay, where one reaction leads to another reaction. So the decomposition reaction we saw earlier made oxygen. Okay, there's a whole bunch of reaction that we saw that has oxygen as a product. Well, these oxygen can be used to drive this reaction, because this reaction is based on reacting with oxygen. Let's fill in some of these blanks. Okay, so most of the fuel we burn. This is important. When we say we burn, let's think about this as reacting with O2. So I don't want you to think fire, even though that's true. Okay, matches, lighter, and stuff like that. Don't think about that. When something burns, it's reacting with oxygen. Especially when hydrocarbons burn. What are hydrocarbons? Well, they're fuel. Okay? The stuff that you put in your barbecue tank, they're called propane. That's a hydrocarbon. Okay? The gas that goes in to your furnace called natural gas, that's a hydrocarbon. The gasoline that you put into your car, your vehicles, that's a hydrocarbon. What's hydrocarbon? Well, these compounds consisted of carbon bonded to hydrogens. And the ratio of this is pretty indefinite. All right, let's fill in these blanks. When a substance burns, it is rearranging bonds, which is really what a reaction is all about, right? Reaction is about breaking bonds and making new ones. You can say that that's rearranging of bonds by reacting with oxygen. Okay? This process causes energy that was stored in these bonds to be given off. Okay? So when you're stepping on the gas panel, what's happening is that these hydrocarbon is breaking apart. Bonds are broken. New bonds are made. Energy gets released because burning of hydrocarbon is an exothermic process, meaning that energy requires to break bond is slower than the energy that you get from making these new bonds. So in a net, you have a release of energy. You get more energy making than investing in breaking. Hey, you don't know what I'm talking about? Unit 5, okay, topic 5 is when we're going to talk about this, in great detail. All right, what does it produce? Okay, it produces carbon dioxide and water. Okay, does it always produce carbon dioxide and water? No, not always. There are times, dangerous times, where it doesn't. Okay, because the amount of products, that is available determines the type of reaction. Oh, sorry, what am I talking about? It's the amount of reactants, usually O2, that is available determines the type of reaction. I'm sorry, not products, but reactants. And we'll see that right now. Okay, in two types of combustion reaction. We have complete combustion. In complete combustion, we're seeing that the hydrocarbon are burned in the excess of oxygen gas. That means there's lots of oxygen gas, unlimited amount of oxygen gas, oxygen everywhere, unlimited supply. Well, what are you going to get if you're burning hydrocarbon in an excess of oxygen? You're going to get exactly what I said you're going to get. You're going to get carbon dioxide, which is CO2, and you're going to get water. Think about it, it's pretty clean. Well, it's really not that clean to the environment because you can see both carbon dioxide and water are greenhouse gases. They do tends to, store energy, from the sun and release it in the form of heat, causing the temperature of our atmosphere to go up. We know that. Okay? We heard of global warming. We heard of climate change. Now, let's take a look at two reactions here. This is called methane. This is exactly what's happening in your furnace, in your basement. Natural gas. This stuff is called propane. This is the gas that you use to fry your hamburgers in the summertime. Think of it. I kind of want a cheeseburger right now. So if you take methane and you react it with oxygen, assuming the fact that you have an excess of oxygen, lots of oxygen, because you're doing this in open air, right? You're going to get carbon dioxide and you're going to get water. Don't forget to balance it. If you're combusting propane, hopefully again in open air, you're going to get carbon dioxide and water. You're always going to get carbon dioxide and water. Okay? And again, Don't forget to balance it. Okay, so these are complete combustion. Now, notice what I said for both cases. I said in the assumption that you're doing this in open air. Open air, meaning the outdoor, not in your garage, not in your... Well, you are doing this in your basement if you think about it. Okay, but it wouldn't be wise to be barbecuing in your garage or maybe barbecuing in your house with the windows closed. That's not a good idea. So those of you who loves hot pot, which I do a lot, where you're kind of, burning those canister propane, you really should have your windows open. You really should. Because if you don't have enough of this, if this right here is scarce, that means not enough. The product is going to be different. You're not only going to get carbon dioxide and water, but you're also going to get this stuff called carbon monoxide. Now, this stuff is dangerous. And you're going to get elemental carbon. Okay? This stuff is dangerous. This stuff can bind to your red blood cell and cause suffocation. The reason is very simple. Your red blood cell contains this protein, this quaternary protein, okay, known as hemoglobin. Hemoglobin, okay, is attached to an iron that should attach to oxygen and deliver this oxygen to cells that needs oxygen, like your brain, man. Your brain needs oxygen all the time. So whenever you inhale, the oxygen get picked up by the red blood cell, and the red blood cell will deliver this oxygen to a cell that needs it. Could be a muscle cell, could be your nerve cells, could be your brain cells, could be any cell. Whatever cell that needs oxygen, your blood will deliver it to it. However, carbon monoxide, this guy can sit in that same spot that oxygen sits. So if you're breathing this in, your blood will pick this up, and your blood will bring this to a cell that don't need this. So you're actually taking up the space for oxygen to be delivered. That's how you get suffocated. And that's how people get poisoned by carbon monoxide. And you should have a carbon monoxide detector in every floor of your house, and make sure it has batteries, man. All right, this is poisonous. Okay, carbon monoxide. So here's a couple of incomplete reaction. Incomplete reaction, nobody will ask you to balance it because it kind of makes no sense to balance these things. Okay, because you don't have a complete supply of reactants. So the products that you're going to get are water, carbon dioxide, carbon monoxide, and elemental carbon. All right. So again, you have your incomplete combustion and complete combustion. So make sure you know the difference of the two. Obviously, you have to be told if enough oxygen is given to generate these two type of reactions. Now, I'm gonna do another reaction here, some extras. This one is called cellular respiration. Okay, this is exactly what's happening in your cells. Okay, it's probably better if it's inside a mitochondria, because what you're doing is that you're taking sugar and you're reacting it with oxygen gas to give you carbon dioxide and water. Okay, so that's cellular respiration. Looking at this is very similar to your complete combustion, except this reaction is not a one-step reaction, and your biology teacher will let you know that this reaction composes of a couple of pathways. Number 4, combustion of alcohol. So let me give you an example here. Here's an alcohol called methanol. If you react this with oxygen gas, you're also going to get carbon dioxide and water. So those are combustion reactions. So the next time, we're going to look at the displacements. We're going to first start with single displacement, followed by double displacement. Okay? All right, let's call it for today. Bye, guys.